Dear students, today we are starting the lectures on oil and gas processing, and the topic of the first lecture is refinery products. Today we will discuss 5 issues, which are overall refinery flow, low boiling products, gasoline, fuels, oils. Modern refinery operations are very complex, and to a person unfamiliar with the industry, it seems to be impossible to reduce the complexity to a coordinated group of understandable processes. The typical fuels refinery has a goal: the conversion of crude oil into transportation fuels. The high volume profitable products are the transportation fuels such as gasoline, diesel, and jet fuels, and the light heating oils. The left bottom side of this slide, you can see the image of typical oil refinery plant, and the process flow and products for a complete refinery of high complexity are shown in figure at the right of this slide. The processing equipment indicated in this diagram is for processing crude oils of average gravities and sulfur contents. Crude oils with high specific gravities and high sulfur contents require additional hydrotreating equipment. The crude oil is heated in a furnace and charged to an atmospheric distillation tower, where it is separated into butanes and lighter wet gas, unstabilized light naphtha, heavy naphtha, kerosene, atmospheric gas oil, and topped or reduced crude. The topped crude is sent to the vacuum distillation tower and separated into vacuum gas oil stream and vacuum reduced crude bottoms, residuum. The reduced crude bottoms from the vacuum tower is then thermally cracked in a delayed coker to produce wet gas, coker gasoline, coker gas oil, and coke itself. Without a coker, this heavy residue would be sold for heavy fuel oil or asphalt. The atmospheric and vacuum crude unit gas oils and coker gas oils are used as feedstocks for the catalytic cracking or hydrocracking units. These units crack the heavy molecules into lower molecular weight compounds, boiling in the gasoline and distillate fuel ranges. The products from the hydrocracker are saturated. The unsaturated catalytic cracker products are saturated and improved in quality by hydrotreating or reforming. While the average consumer tends to think of petroleum products as consisting of a few items such as motor gasoline, jet fuel, home heating oils, kerosene, etc., a survey conducted by the American Petroleum Institute, or API, of the petroleum refineries and petrochemical plants revealed over 2,000 products made to individual specifications. Table 1 shows the number of individual products in 17 classes. In general, the products which dictate refinery design are relatively few in number, and the basic refinery processes are based on the large quantity products such as gasoline, diesel, jet fuel, and home heating oils. Knowledge of the physical and chemical properties of the petroleum products is necessary for an understanding of the need for the various refinery processes. The petroleum industry uses a shorthand method of listing lower boiling hydrocarbon compounds, which characterize the materials by number of carbon atoms and unsaturated bonds in the molecule. The classification of low boiling products encompasses the compounds which are in the gas phase at ambient temperatures and pressures. These compounds are, for example, methane, ethane, propane, butane, and the corresponding olefins. Methane is usually used as a refinery fuel, but can be used as a feedstock for hydrogen production by pyrolytic cracking and reaction with steam. Ethane can be used as refinery fuel or as a feedstock to produce hydrogen or ethylene, which are used in petrochemical processes. Ethylene and hydrogen are sometimes recovered in the refinery and sold to petrochemical plants. Uh, Table 2 presents physical properties of paraffinic gas, paraffins in crude oil. The next gaseous compound is propane. Propane is frequently used as a refinery fuel, but it is also sold as a liquefied petroleum gas (LPG), whose properties are specified by the Gas Processors Association. The butanes present in crude oils and produced by refinery processes are used as component of gasoline and in refinery processing as well as liquefied petroleum gases. Normal butane has a lower vapor pressure than isobutane, and it is usually preferred for blending into gasoline to regulate its vapor pressure and promote better starting in cold weather. Regulations promulgated by the Environmental Protection Agency to reduce hydrocarbon emissions during refueling operations and evaporation from hot engines after ignition and turn off have greatly reduced the allowable rate vapor pressure of gasolines during summer months. This resulted in two major impacts on the industry. The first was the increased availability of N-butane during the summer months, and the second was the necessity to provide another method of providing the pool octane lost by the removal of the excessive N-butane. N-butane has a blending octane in the 90s and is a low-cost octane improver as gasoline. When butanes are sold as LPGs, they conform to the GPA specifications for commercial butane. Butane propane mixtures are also sold as LPGs or liquefied petroleum gases, and their properties and standard test procedures are also specified by the GPA. Average properties of commercial propane and butane are given in Table 3. Most refiners produce gasoline in 2 or 3 grades: unleaded regular, premium, and super premium, and in addition supply a regular gasoline to meet the needs of farm equipment and pre-1972 automobiles. The principal difference between the regular and premium fuels is the anti-knock performance. Gasolines are complex mixtures of hydrocarbons having typical boiling ranges from 38 to 205 degrees centigrade as determined by the ASTM method. Components are blended to promote high anti-knock quality, ease of starting, quick warm-up, low tendency to vapor lock, and low engine deposits. Light stain around gasoline consists of the C5 88 degrees centigrade fraction of the naphtha cuts from the atmospheric crude oil. C88 degrees centigrade fraction means that pentanes are included in the cut but the C4 and lower boiling components are excluded. And the temperature of boiling point end points is approximately 88 degrees centigrade. As a result, it is processed separately from the heavier straight-run gasoline fractions and requires only caustic washing, light hydrotreating, or, if higher octanes are needed, isomerization to produce a gasoline blending stock. For maximum octane with no lead addition, some refiners have installed isomerization units to process the LSR fraction and achieve PON octane environments of 13 to 20 octane numbers over that of the LSR. Catalytic reformate is the C5 plus gasoline product of the catalytic reformer. Heavy straight-run HSR and coker gasolines are used as feed to the catalytic reformer, and when the octane needs require fluid catalytic cracking and hydrocracked gasolines of the same boiling range may be produced by this unit to increase octane levels. The reformer increases the octane by converting low-octane paraffins to high-octane aromatics. Some aromatics have high rates of reaction with ozone to form visual pollutants in the air, and some are claimed to be potentially carcinogenic by the EPA, Environmental Protection Agency. Restrictions on aromatic contents of motor fuels will have increasing impacts on refinery processing as more severe restrictions are applied. This will restrict the severity of catalytic reforming and will require refiners to use other ways to increase octane numbers of the gasoline pool by incorporating more oxygenated in the blend. Polymer gasoline is manufactured by polymerizing olefinic hydrocarbons to produce higher molecular weight olefins in the gasoline boiling range. Alkylate gasoline is the product of the reaction of isobutane with propylene, butylene, or pentylene to produce branch-chain hydrocarbons in the gasoline boiling range. Normal butane is blended into gasoline to give the desired vapor pressure. The vapor pressure of gasoline is a compromise between a high RPVP to improve economics and engine starting characteristics, and low RPV VP to prevent vapor lock and reduce evaporation losses. Concern over the effects of hydrocarbon fuels usage on the environment has caused changes in environmental regulations which impact gasoline and diesel fuel composition. Field testing indicates that it is desirable to have gasoline sulfur contents of less than 300 ppm, as it is shown in table 4. The fluid catalytic cracker, naphtha, is the main source of sulfur in the refinery gasoline pool. The alternative is to hydrotreat the FCC naphtha, but this saturates the olefins in the naphtha and results in a blending octane reduction of 2 to 3 numbers. The sources and reactivities of some of these gasoline components are shown in tables 5 and 6. Specifically, xylenes and olefins are the most reactive, and it may be necessary to place limits on these materials. Distillate fuels can be divided into 3 types: jet or turbine fuels, diesel fuels, and heating oils. These products are blended from a variety of refinery streams to meet the desired specifications. The The consumption of heating oils has ranked high in the refinery production goals, but as a percentage of refinery products has been decreasing because of increases in gasoline, diesel, and jet fuels in recent years. Jet fuel is blended for use by both commercial aviation and military aircraft. It is also known as turbine fuel. Jet fuel is blended from low sulfur or desulfurized kerosene, hydrotreated like coker gas oil, and hydrocrack blending stocks. The ignition properties of diesel fuels are expressed in terms of cetane number or cetane index. These are very similar to the octane number, and the cetane number expresses the volume percent of cetane in a mixture with alpha methyl naphthalene. Although the consumption of petroleum products for space heating ranks very high, the consumption varies widely according to locality and climate. In recent years, the proportional demand for heating oils has decreased and LPG uses has increased. The principal distillate fuel oils consist of number 1 and number 2 fuel oils. Number 1 fuel oil is very similar to kerosene, but generally has a higher pour point and end point. Limiting specifications are distillation, pour point, flash point, and sulfur content. Number 2 fuel oil is very similar to number 2 diesel fuel, contains cracked stock, and is blended from naphtha, kerosene, diesel, and cracked gas oils. Limiting specifications are sulfur content, pour point, distillation, and flash point. Most of the residual fuel oil used is composed of the heaviest parts of the crude and is generally the fractionating tower bottoms from vacuum distillation. Critical specifications are viscosity and sulfur content. Sulfur content specifications are generally set by the locality in which it is burned. Heavy fuel oils with very low sulfur contents are much in demand and sell at prices near those of the crude oils from which they are divided. At this slide you can observe 5 questions which you are asked to answer by the next week. In order to get acquainted with more information concerning this topic, you may use the literature which is listed in front of you. And that's all for today. The lecture is over. Goodbye.